I will start by thanking the organizers for inviting me here. Thank you very much for giving me the opportunity to talk about calibration for climate model during this meeting. I also would like to thank quite a few collaborators here: Daniel Williamson, Fleur Couvreux, Frédéric Ourdin, Olivier Audouin, James Halter, Najda Villefranc, Victoria Volodina, and Wengze Xu, because they help a lot in developing the tools that are at the heart of what I'm talking about today. So maybe for those that don't know what climate models are, maybe not a lot, just a few reminders. So developing a climate model, start by choosing a set of equations from the fluid dynamics, the thermodynamics, with some approximation like the thin layer, the OceaniX approximation, and so on, and then to discretize those equations on the sphere to solve them numerically. This discretization introduces a model resolution. There is a choice here to do with the with some processes that will be explicitly resolved by what we call the dynamical core of the model, and some processes that won't be resolved, like the small movement of within the atmosphere, like convection and so on, which need to be parameterized because they have a lot of impact on the result scale. You can note that some processes still need to be parameterized, whatever the resolution used, like radiation or the microphysics within the clouds. Once we have done that, in fact, here it's an example of the relevant processes for the atmosphere, convection, clouds, interaction with radiation, etc., etc. In fact, it's not specific to the atmosphere. It also, we have the same kind of issues, same kind of approach in ocean model, in sea ice model, in non-surface atmosphere model, non-surface model, etc., etc. So we do that for each component of the climate system, and then we have to couple the component model together with some issues in terms of information exchanges. So when we have these models developed, the problem of calibration emerge. So first, just remember that the climate model is some kind of software to which we have to provide external forcing. As I explained, we have to define a grid, so horizontal and vertical. And then we have what we can call a scientific content, either for the fluid dynamics equations that are used, but also for all the parameterization, the processes that are parameterized, which effect on the larger scale is parameterized. And when we develop those parameterizations, there are a lot of approximations, simplifications that we made, which as a result may emerge what we can call parameters, internal or uncertain parameters, which are the lambda p here, which need to be calibrated, meaning that we need to choose a value, possibly one of the best value, to have a good model, a skillful model in the end. So calibration is not specific to climate model, it's common to most modeling frameworks. First, it was probably seen as a kind of optimization procedure given a certain number of constraints or metrics, to which we can give some priorities or weights. Of course, in this process of calibration, we need references, observation to define the targets, possibly high quality references, observation, or possibly with well quantified uncertainties. And as an example about the importance of calibration is that an important metrics for climate model is to have a top of the atmosphere budget at equilibrium or close to equilibrium. And just meaning that we need to achieve the top of the atmosphere budget within less than 1 watt per square meter, because in the end, if we have just out from 1 watt per square meter out, it means that at the surface, the mean global temperature is about plus or minus 0.5 to 1.5 Kelvin out from the observations. So even with what we can do today with spatial observation of the top of the atmosphere budget. Given the uncertainties we have with the measurements, the present day climate global mean temperature in a climate model is mostly a result of the tuning. So it's really important to address calibration in climate models to get skillful and useful climate models. So why is it a bottleneck for climate model development? So first, within the set of parameterization we are using climate models, there are quite a large number of parameters, a few tens in general. So it's a high dimensional problem, at least for the human brain. Climate model numerical simulation are expensive. To do a 10-year simulation, it takes a few hours, depending on the resolution of the model, so that an exhaustive exploration of the parameter space is not directly possible. Also, the number of metrics is pretty large and pretty various. Some are rather subjective, meaning that it's difficult to quantify them. So it's another problem in terms of dimensionality. We have the overfitting issue. Often we don't really know what we can call the structural error of the model, what it can really do given the approximation we have made in it, or given the missing processes in it, so that it can lead to overfitting, often in terms of compensation of error between different processes. And also we need to treat the uncertainties well, because it's important for climate projection to be able to provide a relevant uncertainty on for the projections. Sorry. So for the CNRM CM6 model, so that this is a model we prepare for the CMIPSIS exercise a few years ago, which is a model intercomparison project at the international level. We did it over a few years, doing manually, because we didn't have at that time tools to address it in a more relevant way. This is the subject of the talk. So manually, meaning that we take one or two parameters at the same time, play with those parameters to see how the model behaves, and say, so to go in that direction for given metrics, I need to vary my parameters this way, and so on. And so from one step to the other, we managed to arrive to some kind of skillful model using quantified metrics, but also more subjective consideration in terms of model behavior. So climate model, as I say, it's different components, like an atmospheric component and ocean component in particular. So the calibration was done on each side before coupling the model and continuing the calibration of the coupled system. And of course, we had to set priorities about the metrics that I will come back a bit later. Of course, it's a problem of calibration, but it also questions a lot what we have put in the model. Can we really have a skillful model for a given process or a given metric without having very worse, very bad behavior for other metrics? So it's also a way to better understand the structural limits of the model. So given this rather manual approach during the few recent years, we define a rationale for addressing this calibration bottleneck based on three features. The first one is to use what we call history matching, which means that we don't want to optimize the system because we want to avoid overfitting issue, or we want to consider the various uncertainties that we have during the process of calibration. But we want to determine the plausible sets of model parameters given a set of quantitative metrics. Or to say it another way, we want to rule out the implausible sets of model parameters values. So for a given set of quantitative metrics, for considering references or observation uncertainties, and introducing some prior for model structural errors, which we will interpret here as tolerance to error, because it's quite a huge problem to have a prior ID on this structural error of the model. But hopefully we expect that we learn something about that in the course of model calibration. So then we use machine learning to emulate the model behavior. That means the dependence of a given set of metrics to model parameters, to explore at very weak cost most of the parameter space that we need to explore. Of course, we want to consider the emulator's uncertainties in this process. And that's why it was chosen to use Gaussian processes, because they nicely provide prediction with an uncertainty estimate for them. And then the last feature is what is called iterative refocusing. And the idea is that because the models, the true model simulations that we need to do to prepare a learning data set for machine learning techniques are expensive. So we want to be as parsimonious as possible in terms of true simulations that we will need to do in the end. So the idea is to start with a few simulations and progressively add new ones to improve the emulator quality, but only where it's really needed. So that's why we want to roll out some part of the space where we know, given the uncertainties, that the model is not skillful in that part, and add new simulation where it's interesting to have them to increase the emulator prediction capabilities. And in this iterative refocusing process, we can, along the way, we can add a new matrix or new configuration of the model, or more expensive, especially more expensive simulation, because we can precondition the parameter space to explore with cheaper configuration. So in the end, I will try to show you in the rest of this talk that we have a formalized calibration procedure, which is transparent and reproducible. That was not really the case when we do it manually. It was really dependent on the person that was doing the job. We have a semi-automatic and efficient framework, which allows us to quantify the true benefit of a new development more rapidly. We can do more rigorous comparison between parameterization and model physics in terms of behavior in the full system. And in the end, we will maybe not have just one single acceptable configuration, but several, which is interesting in terms of quantifying uncertainties for many emergent properties of the model, and especially climate projections. So more about the technical framework. So we define targeted metrics, which so far are only scalars. We have to define the reference value and the associated uncertainties. Then we identify in the model the relevant parameters that we want to calibrate, and we define an acceptable range by expert judgment. And this is what I will call the input parameter space. Then we have to define a simulation strategy to build an experimental design and run true simulation to provide a learning data set for the machine learning component. So then from this learning data set, we can fit Gaussian processes to emulate the dependence of the metrics to the model parameters. And from that, we can identify the subspace of the input parameter space, which is compatible with the references for all metrics. I will call it the not ruled out yet space, or NY space. Considering in that the reference uncertainties, the emulator uncertainties, and the model structural error, which, as I said, is interpreted so far as a tolerance to error. This provides an implausibility measure, which is defined here. This is mostly the distance of the emulated metric to the reference divided by the sum of the variance, the sum of the uncertainties. So assuming that they are independent. And from that, given a cutoff, which in general is about 3 because of statistical reasons, we can define the NO space as the set of parameters for which the implausibility is lower than this cutoff. And when we have multiple metrics, it's simply the intersection of the space of each matrix. So here we have history machine and machine learning, and the iterative refocusing. It just, in the end, further sample the first not ruled out yet space that we have with new sets of parameterization of model parameter for which we want to increase the learning data set. So make new simulation, emulate again, increase the Gaussian process quality within the previous not ruled out yet space, and do that until we have some convergence. So first, the first application I will show you is using what we call 1D configuration of the model, or single column model configuration. Why we do that? It's because when we develop parameterization, we like to have references with as much of data as possible on large eddy simulation, which explicitly resolve the process that we want to parameterize, are really interesting for that because they inspire the development of atmospheric parameterization. They help to validate the development that we do, and of course to calibrate them. So the first case I will use is the diurnal cycle of a continental cumulus case that occur over the Great Plains of the US. So here you have the large eddy simulations of the reference. You see that you have this cumulus that develop across the day, and this is what the standard configuration of the model is doing. So it's not that good. I mean, we have too much cloud. The cloud base is a bit too low. The boundary layer here is potential temperature at after 10 hours of simulation. You see that it's not deep enough. We have too weak mixing with the free troposphere, and for the specific humidity, you see that we have some issue probably with numerical issues, and some also intermittency in the activation of some processes across the simulation. So the question we ask is, this error, is it due to poor calibration, or is it really intrinsic limit of the model that we need to reduce? So I will just take the technical framework as I provided earlier. So the calibration setup, we are using 14 metrics for temperature and specific humidity and cloud fraction at a few levels, the 10th hour of the simulation. So here you have the different levels that we are using. The reference is large eddy simulation done with the MesoNH model at CNRM, and for the uncertainty, we have an ensemble of large eddy simulation done with MesoNH, but with varying the resolution of the model with and some of its parameterizations. In the CNRM model, so we have 26 parameters, 13 are relating to convective transport, 2 to convective closure, 1 to convective cloudiness, 6 to the liquid water microphysics. We only have liquid water in those clouds here, and 4 to the turbulence parameterization. For the first wave, I will do, and for the other waves, I will do only 200 simulation that are first sampled using a Latin hypercube. And as I said, for the next wave, for the iterative refocusing, so it's also 200 simulation, but which are within the previously identified not ruled out yet space in the model. So after wave 1, so the first learning data set that we have, you see that we have quite a variety of behavior. Some simulations are good. This is, as an example, the blue line, and some are really far from what we would like to achieve. Here I put what I defined for the tolerance to error in the process that is used across the refocusing. After 33 wave, so we have reduced the variability within the simulations that are within the previous wave. We have a lot of configurations that are much better than the default. The default, the red line. The convergence is not fully achieved. We see that we have quite a few simulations, especially for the cloud fractions, that are rather far from the references. And we see that we have probably some interesting limit of the model physics with this numerical instabilities in the profile of specific humidity. So that it means that we need to work on the model physics itself and the way we discretize the equation in them. So just a few words about the evolution of the not full yet space and its convergence. So here you have the error space fraction of the input space. So we see that we have reduced the input space by almost 6 order of magnitude. So we start with a cutoff of 3, as I said, which is quite conservative. And when we think either that the uncertainty of the emulator is weaker than the tolerance to error of the reference uncertainty, we can reduce it, or because we think also that the size of the error space is approximately stable. So in the end, after 33 waves, as I said, we have reduced the input space by more than 6 order of magnitude, which start to make it quite difficult to explore it, because it means that if you just randomly select 10 to the 8 configuration of the model, only 290 configuration will likely be in the error space. So we have to explore quite a tiny space to characterize it. And just about the convergence a bit more. So here you have the from a leave one out approach, we have the Gaussian process standard deviation for the distribution. So we see that it mostly decreased along the process. The blue line is the sum of the reference uncertainty and the tolerance to error. So in this case, for potential temperature at 200 and 2,500 meters, we have below, so we have some convergence, but for cloud fraction at 1,300 meters, it's still are comparable to the reference and tolerance to error uncertainties. So it's difficult to imagine how this space looks like, and we have no equation to document it, so we have to characterize it numerically. This is what is done here. I won't go into detail, but just to give you the kind of diagnostics we can produce to analyze it. So we do a very large sampling of the input space using a Latin hypercube sampling. We use the emulators to compute the associated implausibility, so it goes quite fast, at least compared to the model. And we compute the density of points within the error space as a function of the parameters. And here we have a 2D representation. So for each panel, you have the dependence between 2 parameters, and you have the density or the optical depth of the parameters that are plausible given the metrics we are using, the constraint we are using. So here, just a zoom for the dominant parameters. So the 6 dominant parameters, 3 are related to the turbulent mixing and dissipation, 1 about convective cloud fraction, and 1 about entrainment. And we see that we have quite reduced the possibilities for calibration, and that the red dot, which is the default model, is not within the error space. This is not surprising given the result I showed earlier. So we see some dependence between parameters, which are interesting and which reflect some physical behavior. And interestingly, for the entrainment in convection, which is an important parameter when we model convection in the atmosphere, we see that we need high entrainment rate for this shallow cumulus case, which is consistent with the literature. So if I just extract one simulation from one configuration from this error space, here you have an example. So we see we have improved quite significantly the result of the model for the cloud fraction. This is also the case for the specific humidity and the temperature across the simulation, not only at the 10th hours. And here you have some internal parameters which were not part of the calibration process, and we see that we manage also to constrain them. So the blue line is the improved version. The red dots, the dots are different estimate done with a large dissimulation for those parameters, for the updraft area fraction, the updraft vertical velocity, and the updraft buoyancy. And we see that we improve quite significantly the response of the convection parameterization without taking into account these internal parameters. So from that, so I show you that we can have a better calibration of the model for these specific shallow cumulus cases. One of the questions we have in the course of developing the CNRM CM6 model was the following. In fact, we use what we call a unified approach, meaning that we want to represent both shallow and deep convection with the same parameterization. But in all the course of the model development, we were always asking ourselves, is it a good choice? Can we really do that with the formulations that is in this parameterization? And this is what I want to address. Can we use this unified approach to model shallow and deep convection at the same time? So to do that, so I have this shallow convection case I was using before. I'm adding a deep convection case now, which is based on the field campaigns that occur in 2011 in the Indian Ocean. And you have here the potential temperature bias of the model and the specific temperature bias of the model. And here the evolution of precipitation. So we have 3 phases of the so-called Madden-Juliet oscillation in the Indian Ocean, where convection is active with precipitation and suppressed phase in between. So in the following, I will just focus on the first MGO event from 15 October to 4th of November. So as previously, I defined metrics. So it's based on temperature, specific humidity, and relative humidity profile average over the full event. So reference is not large simulation. We don't have this kind of simulation for this case, but we have observations that were done at the scale of a given array. So I'm using that. For the parameters, this is the same as previously, but I'm adding new parameter because in this case I have high microphysics active and radiation is also active. That was not the case before. And I'm following about the same approach with 200 simulation in the end. And as I said, the objective is to improve the mean, to calibrate, to do calibration using the 20-day average temperature, specific humidity, and relative humidity profiles. So after wave 29, so we don't have full convergence, unfortunately, but the space starts to be small. It's 5 order of magnitude smaller than the input space. Not the same parameters that are active compared to previously. Here we have the convection entrainment, but the convection closure appears. Also, the evaporation of rainfall start to be really important, which is in particular the case for the moisture vertical profile. And we also have the ice autoconversion process that appear, meaning that the life cycle of ice cloud, and in particular in this case, high-level ice cloud, and the way probably they interact with the long-wave radiation is important to get the profiles. But just if I compared, so in the shallow convection scheme, in the shallow convection case, I had these 2 parameters also active. And if I do a comparison, we see that there is a very weak overlap between these two cases, meaning that it's probably impossible to be able to reproduce the 2 cases at the same time with the same set of parameters. So just what did we learn from this 1D configuration? So first, I think history matching with iterative refocusing provide a framework to rigorously explore the parametric calibration of a parameterization or model physics and start to identify the structural limits. And this is helpful for model development. I show you that we can achieve a better tuning of the CNRM convective parameterization, either for a shallow convection case or either for a deep convection case. But achieving that for the two shallow and deep convection case at the same time doesn't seem to be feasible, at least given the tolerance to error I used. So that the conclusion here is that the CNRM-CM6 model single plume mass flux approach is structurally limited. And in particular, I didn't say that, but shallow and deep convection in this case require significantly different entrainment rates. High entrainment rates for shallow convection, weaker entrainment rates for deep convection, and this is consistent with what the literature has found also. So this was quite an idealized framework using 1D configuration, but what can we learn about the model in more realistic configuration, and I mean 3D configuration? So just to start, this is a kind of model bias or metrics we want to address and reduce when we develop a model and when we calibrate it. So here you have the cloud relative effect at the top of the atmosphere for the short wave and for the long wave as a map, and here as an average over all longitudes. Here you have precipitation biases for winter and for summer, and here it's also averages over the latitude. Just here you have the zonal average of the annual temperature as a vertical profile. So we see we have quite a large cold temperature bias in the free and upper troposphere. We have too few clouds in the eastern part of the ocean basin in the subtropics, also in the austral summer. We have some issue in the long wave. We don't have enough precipitation over the continent, and especially South America, Africa, and the maritime continent. And this is a kind of, so this is what we achieve in developing the model, but this is the kind of model issues that we would like to see if we can reduce them. So can we reduce this kind of biases through a better calibration? So the metrics are rather different, and we can start to have some kind of priorities, at least in the term we address them. So when we develop a climate model, the first metrics that we want to have well is global averages, to have the right energy budget of the model at the top of the atmosphere, at the surface, at the same time, because we want to couple the model to the ocean. As a reference, we use spatial observation with some uncertainty derived from the literature, except at the net energy budget at the surface or at the TOR, where we think that the observations are not good enough to constrain it. So we make quite a strong constraint because we want the model to be equilibrated. So this is the first priority when we want to have a zonally average profile rather well, because it's important for the large-scale circulation, still for the radiation component, especially clouds, but also for the temperature in the upper troposphere. And then, as a third priority is to get regionally features rather well. So also for the cloud relative effect in short wave and long wave, but also for precipitation, and depending also on the seasons. So as I said, we are only emulating scalar metrics, so we are doing averages over quite a lot of domains where we would like to improve the models. So far we have 63 scalar metrics, 46 model parameters. So this is approximately the same as before. So usually the map I showed you, it's based on 30-year simulation. It's too heavy to do that in the calibration exercise, at least at the beginning. So we have to find a way to accelerate the process, and we are To do that, we are using what I will call SST clean. So we are using climatology of sea surface temperatures to prescribe the model. Only 1 year simulation, because we think that for many of those metrics, we don't have a too large internal variability. Still, we want to account for this internal variability, so we have tried to quantify it and to account for it in the implausibility measure. We are also, because SST clean is not the same configuration that we are using usually to calibrate the model, we need to apply some correction of this approach, because we don't have exactly the same behavior of the model. And as before, for the first wave, we are sampling using a Latin hypercubes. So after wave 1, this is for a few of the dominant parameters, what the not ruled out yet space look like. We have a few parameters that are related to the ice cloud processes and also convection. So this is what we are used to. If we go further, so in this case, I'm doing only 8 waves because it's computationally expensive. We have a large shrinking of the NO space, 8 order of magnitude. So we start to really explore a tiny volume in the full parameter space, which is quite difficult. Some metrics are rather converged, meaning that they are comparable. The uncertainty of the emulator is comparable to the uncertainty of the references or the tolerance to error. For some, still not converge. So still need to be explored, or at least to do with that if we don't have any more computing resources. Of course, the space is much smaller. We don't have so much freedom for some of the parameters, but we also see it's not here, but starting from the dominant parameters in the full at the wave 1, after a few waves, it's not always the same. We have new dominant parameters that emerge, which is important to have in mind, to not reduce the number of parameters at the beginning, but to let discover which parameters are really important in the end. So unfortunately, after these 8 waves, there is no simulation that we have performed to build the emulators that fulfill all the metrics. Of course, we don't have convergence, so it doesn't mean that it doesn't exist. We have some issues to appropriately sampling the small volume of the NO space at this time. This requires further work. And probably some tolerances of errors that we have prescribed at the beginning are a bit too weak, and we need to revisit a bit them. Nevertheless, we can there is a few simulations that are interesting, at least because they fulfill all the metrics but one. So we'll just show you a few results with some of these simulations. We also have a few simulations that have rather low root mean square error compared to observation for the targeted variable I'm using. So for this identified set of parameters, I'm doing 10-year MX style simulation, so rather the true simulation we are using usually. So here you have an example of the improvement or similar behavior compared to the model. So it's a bit improved for the cloud relative effect. If you look at the RMC, for instance. For precipitation, it's harder to see, but what is interesting is that we reduce quite significantly the biases over the continent, the dry bias over the continent. It seems that some errors are really structural. This is not new, but it's confirmed at the process that it's difficult to get the clouds over the eastern part of ocean basin, stratocumulus or stratus. Maybe I will skip that. It's just a way to condensate the information to look at the quality of the simulation. And we see that it's similar or better than the reference simulation. Maybe an interesting, it's, as I said, for the 1D configuration, we can also assess some structural limits of the model. And here it's an interesting one for the temperature at the top of the troposphere. So in green, you have the wave 8 simulation. So in black, this is a reference, so we are quite far. What is interesting is that at the beginning, at the first wave, we can have a few simulations that are closer to the observation, but they disappear across the successive wave, meaning that they are incompatible with other metrics that we are using. And in fact, when we just take the mean value of this trend and the mean value of this trend and put them together, in both this is uncertainties we are putting, and we see that most of the points are outside the range, and we cannot get at the same time the temperature in the tropics and in the Arctic, which is likely a structural limit of the model. So just as a form of conclusion, so I have worked in 1D configuration, in 3D configuration, but of course we would like to be able to connect these two frameworks, and in particular because at the 1D level we are close to the process, and we think that starting the calibration at this level is a good way to keep the process well represented while preconditioning the calibration of the full model or more realistic configuration of the model. Of course, to do that, we need to have high quality references, either observation, large eddy simulation, or convection permitting simulation for the targeted processes. So sometimes it's available. It's the case for boundary layer clouds, boundary layer convection, for stable boundary layers. Some are currently being developed, especially when it involves radiation. For some other, it's still an open question to what we should use, such as the case for microphysics. So there was a proof of concept with LMDZ in this paper of Ourdin et al. 2020, where he combined the 1D approach in the first step, do 30 wave in this 1D configuration, then add new metrics using the full 3D model, either global or regional, a bit in the same spirit as I was doing before. And for the 3D configuration, only 2 waves were done. So it works well in 1D. I won't go in detail. There is some interesting analysis to understand what is happening in terms of processes. And then when we start the 3D, so starting from what the 1D configuration has given, so this is red lines. So we see that they are not all over the place. So the preconditioning is working well. It's rather similar in terms of behavior to the LMDZ model calibration that was done by hand. And of course, a few more ways would be helpful, but it's dependent on computing resources. And to go until the end, it was tested in the ocean atmosphere couple configuration. So this is for 2 configurations. So this is the orange line. The default is a red line. So we see that it's improved over the tropics. So this is a bias for the surface temperature. It's not the same, not the case for the more global system, but still, this kind of calibration was done like in maybe 2 or 3 weeks, while the full calibration of the model took 2 to 3 years with previous methodologies. So to conclude, I hope I convinced you that history machine with iterative refocusing provide a relevant and efficient framework for model calibration in the presence of uncertainties. It can help accelerate model development by comparing different calibrated model versions and really understand the impact of the representation of a process on the system. So we assessing the true added value of a new development, not just doing it subjectively as before. The method provides also a framework to identify and quantify model structural error, or to, and this is interesting for model development, to help focus model developers on that. And overall, it questions the scientific content of the climate model. In terms of next steps, of course, we need to pair this tolerance to error to better identify or quantify model structural error and the kind of trade-off we need to make. Add a new metrics, and especially there is a concern in the community: can we get both the mean state of the climate model and its variability right at the same time? So this is clearly something we can start to address in this framework. As I show you, preconditioning using very cheap model configuration is really interesting. For going to ocean atmosphere coupled configuration, it's there is a big step to do because they are more expensive. They need longer time of simulation to achieve equilibrium. So we need method to accelerate spin-off, possibly use intermediate resolution and transfer knowledge between this resolution, and so on. And more on the physical side, we need to develop physical interpretation of what is really going on during the calibration process. Maybe more on the technical or statistical aspect. So as I said, we start to have very tiny volume of the input space that we need to sample to document, and it starts to be really difficult with the method we are using today in those tools. I was using only scalar metrics, but of course we would like to be able to emulate directly vector or maps. And there are a few proposals in the literature. And recently, Wayne J. and collaborators show that we can even emulate the expert judgment, because sometimes it's really difficult to quantify the right metrics. Because, for instance, if I take the shallow clouds, sometimes they just the clouds start earlier by 1 or 2 hours, but still the development is going good. So we would like to capture that, but it's hard to quantify it. And just to ask the expert, is the simulation better than the other? And to make it several times, we can in fact learn what is happening in the expert head and use this in the process of history matching. And that's all. Thank you.